over here.
I'm like, what? Not too early? I must be wrong. So
You said it's gonna be 309 for the evening class. Which one is 309? This one.
here, Rick 302, 12 to, yeah.
Yeah, we're fine. Well, that's weird.
Yeah, very cool.
It's 309. I want to see his camera. I don't know today. That's good, we're good.
There's no one here. I'm not here.
Yeah, that's weird, right?
This one wasn't comfortable.
Yeah, right. Does the other one in another room?
I don't know.
Yeah, that's like 309, I guess. Yeah, here we go.
What are you looking at that, dude?
What's up?
Gonna have dinner?
Cool. Here?
Yeah. The Blasingame, actually.
With Blasingame? But yeah, no, eating.
So he's gonna teach from 4 to 8.
And then
dinner.
No, with him. Yeah, you wanna have dinner with him?
Yeah.
Oh, that's cool. What is
Sorry,
that?
FD.
Oh, because of the price and that?
What price?
We got that metal thing.
Oh, no, not that.
Because what?
I was disappointed, man.
We didn't have the other
Outstanding.
one. What is the other prize that we got last year?
Outstanding.
Outstanding. We didn't have that
No.
one. Who got that one?
I don't know yet, but they don't give it twice in a row.
They don't?
No.
But we did. They gave it to us once in a row, right?
No.
The day before we didn't have
No.
it? Oh, that's the reason why. We got the gold medal though.
Yeah. Gold is 80 or above in the score. So anybody 80 or above goes. And then the best score in North America gets the most outstanding.
Oh,
So like
that's all.
for the AP too?
Yeah. Just ideas in the organization.
What's its middle name? What's the A stand for? Anybody know what the A stands for? I would like to know what the A stands for.
And his middle name?
Yeah.
You should ask him that.
How about you ask him that? How about that?
Except for you, Jeffrey.
Yeah, exactly.
I don't know what it is.
No. He won't explain it from you, so that's why I said.
Oh, really?
Yeah.
But you see the difference is I don't really care what his middle name is.
Yes, you do. You just don't realize it yet.
Oh, Jeffrey, why don't you ask him why he's not using his newer updated photo? Why does he use his old photo?
Yeah, that's a typical Jeffrey question.
No, it's not. Yeah.
On the e-learning.
Yeah,
His old
yeah.
photo.
Yeah.
Who else is going?
What's up?
Who else is going?
No, it isn't either.
Who's that?
No.
Yeah. But I tried to talk to all the stuff.
Everybody has everything. He used to be an FBO by just 5 years.
Yeah. Like, you could apply next year.
Dr. Lam, it's time to work better. And they have the best ideas.
I think
Yeah.
yeah, but
My bail will be blessed. I'm sorry I can't make it.
movie I had one for
Yeah, but it's not for us.
that is bad. Actually, that was
I love me today.
yeah, we had one.
Yeah. Are you going for the 4 hours? I can't make it on Tuesday or Wednesday because my parents are traveling on Wednesday.
Okay.
So I have to make it today.
Yeah. No. But what else?
Yeah, so bad to watch. I tried to miss one. Yeah. The missing lecture of Dr. Jack. I didn't watch it. Like 10 minutes in, I'm like, no. I don't know watch that crap.
I want to watch it first.
I don't know how this is better than Zoom. right? Watching lectures online.
Oh, yeah. Like they've had that for all these.
Right. I think it's just the whole transition to the campus or whatever.
Yeah. Have you looked at the notes for which classes?
Nope. Gonna do that on Tuesday. Oh.
How do you really struggle with it?
Really?
Yeah.
Let me
They're coming to the career fair, but they're not coming to that in
Don't ambush me, go let that fly down.
I'm working with kind of this.
Really?
Sorry, everyone. I was, about to chew my arm off, this guy wouldn't get off the phone. I'm sure you've never done that before. Well, somebody's telling a happy story.
Friday, we have the weekend coming up.
6 hours.
Good idea. I don't know if I believe it.
That's the way I have right now.
What did you really want to be when you grow up?
An engineer.
Wrong game.
Unlikely to succeed.
What's the A stand for?
Figured you know that one by heart. ALWIN is a family name. Excuse me for 1 second, I'm gonna go grab this, figure out what this person told me to do to turn this off. You have an A in your name? So your initials are Jazz?
Oh, wow, that would have been pretty. I should have thought of that.
Alright, so we'll see if this craps it out or not. Okay, somebody complained that they didn't see the discussion on, the start of reservoir engineering being from, the IRS. So we gotta go look at that again. Don't listen to me. Complaint is not the right word. They simply mention. Man, getting old stuff. Jeffrey, did you ever think you were gonna get on?
I'm pretty sure it's inevitable,
Maybe not.
unless that comes before.
Maybe not. I'm just thinking out loud. So July 26th, what's July 26th famous for? Today anybody's birthday? No?
6 hours of Dr. Blasingame's lecture.
Very good. Not sure we'll make it that far, but we'll try. Oh. Sorry, I don't mean to seem so distracted. That call running long, it's really ruined my rhythm. Does that ever happen to you? You got a haircut.
Yeah.
Nice. Where'd you get it done?
Yes, North Gate.
Looks it. I did that one time. Was it the same old guy?
Yeah.
They dig him up from the dead? He did mine, and I remember telling him, I said, this doesn't look right. And he said, it will after you wash it, you know, as though that were somehow going to get me out. Convince me. It looks good. You look like you're in the military. I like it. So any decision on the proposition we have? Yeah, let it grow?
Mohawk.
Not a mohawk. How about a frohawk?
What is that?
What do you think, Rice Grad?
What's a frohawk? What is a
Well,
frohawk?
they let him grow a fro and then we cut the sides off.
Yeah, that was interesting.
That'd be a Mr. T thing. Except you're really not rolling with this, are you?
I don't know what these words mean.
Just grow your house here out really soon, so don't have pizza.
I thought we were gonna have pizza today anyway.
It'll be tonight.
Yeah, that.
I forgot to order. You know, it's pretty bad when your kids know how to order pizza and you don't. And can you order pizza online here?
Yeah.
Yeah.
No problem. I still get some old school. I think you're supposed to like that food. I mean, what's next? You gonna get it through the phone or?
You can actually do that too.
You can already do
No, I meant get the food through the phone.
Oh.
Like a synthesizer, you know? You guys missed the old days before, Domino's, and they showed how somebody delivered a pizza and it was an hour late, and it was stuck to the top of the box. That was kind of cool. You never had one of those? Dennis, you like that? Are you a good cook, then?
I'm pretty good.
As long as it involves peanut butter, bread, and jelly?
Sure.
Okay, so where we were discussing the last time, we went over to this oil and gas monograph from 1918, and it was the United States Internal Revenue Service, or whatever it's called then, monograph. And this is actually the first decline curve. You can see it's figure 1, and they plotted production per year. Please work, yes. Very good. Thank you very much, Victoria. Your idea worked. Okay. And so there's your point. Now, how would you extrapolate this? Now, remember, this is 1918. Bill Gates' father probably isn't even born then. So, any ideas?
Ruler?
Hmm?
A ruler?
A ruler? So you would just do a straight line?
Just getting close to the straight line part of the exponential.
Give me your notebook there. I'm gonna-
I have it.
Oh, you do have a straight edge? You were a good boy, thank you. Despite what Dennis told me the other day. Okay, so you'd say this thing's gonna crap out about right there?
A bit longer.
Okay. Well, we don't know. I mean, how would you feel about a well that went, or just an average curve, but a well that went from 9,500 barrels to 5,500 barrels to 2,500 barrels? That's a huge decline over time. This is back in the good old days. Anyway, we'll, move on down from that. And we'll look at this next one. Yes, I know it's upside down, I was rotated. Okay, so this is another one, and what they did here is they tried to draw an extension. So here's data. And they're drawing some sort of a, you guys ever use a French curve? Hmm? You don't know what a French curve is? When you get older, Jeffrey. If we take a break, I'll bring one. Okay? Now, what are other possible extrapolations? Yeah.
They could go down faster than it.
So we could come off of here. Like that. Over the middle.
Yeah, with a little bit more curve to it.
Okay, so you want yet another one? Something like that?
Bit better.
Okay. Abdallah, you got 403?
Yeah.
Okay. So this might be analogous to a hyperbolic. This might be analogous to an exponential. Can't even write. Let's just say exponential. And then this might be something else. So you're a reserves person in a company. Which one do you want?
Reserve.
The right answer is you want the right curve, but what's going to happen if you're given this dilemma on the job? You will definitely have this on your exam, so everybody needs to pay attention here.
You'll probably figure out that by the time they get to know the real reserves, you'll be way out of the country, so just...
Okay, but looking at this simple case, the red is too low, the blue is too high, and the green is too low, the blue is too high. Is the red just right, or we don't know?
We don't know.
Okay, and in 403, did you guys use that probabilistic stuff where they generate 1,000 renderings of this and basically paint the whole thing black with possible curves? You know, the whole region is painted with curves. So which one's right? And why? This is unfortunately what most reservoir engineers do all day, is they make production extrapolations with very, very little technology behind it. They're using a simplified equation and they're making extrapolations. In order to have something more sophisticated, you have to have a reservoir model tied to it, and we'll talk a little bit about that in the production data analysis section. We're still sort of on pressure transient discussion. But you can see that there's a dramatic, if you're talking about the area under the curve, there's a dramatic differential in these. Yes?
Well, since this is an IRS document, I'm going to assume that you would want the green line in order to maximize revenue over time.
Actually, it turns out that the standards, or whatever you want to call it, went to the SEC, not to the IRS. The IRS doesn't care what it is, they only care that you're not cheating. Okay?
Right.
So they're probably less concerned with that. But the SEC, the Securities and Exchange Commission, which represents essentially any multinational company, they're the ones who are going to say, should you be using a conservative estimate, should you not? And there's a whole host of companies around the world that go in and audit your reserves. And if you've used the blue line, they're probably going to encourage you to push it down. If you use the green line, they're probably going to encourage you to push it up. Pushing it up doesn't happen very often, but it does happen. What happened in 2004 to Shell was a little bit different than this kind of discussion. What happened in 2004 is they declared two assets as reserves, and they did not have active production. And that was disallowed by the SEC. So let's say that we discover the Abdallah field, and we have a well in it, but it's not producing. We can't claim it as reserves. That was the easy part. Now, I think it was Nigeria and Australia where they had these assets. But then they had also gotten their hands slapped because they were being a little bit generous with their decline curve. And this is everybody, not just Shell. It's everybody. There was a company in the late 90s or mid-90s, I can't recall. It doesn't exist anymore, and I won't mention the name. But whenever they had a reserves audit, the auditors could only verify 27% of the reserves. So somebody got really, really liberal with the French curve, or the flex curve. And that is not a good place to be. Yes, sir.
Are these audit reports available to the public?
Not the raw data because that's proprietary, but I'm sure there's an SEC. Everybody files
10K or
exactly. Thank you. I was going to call it something else, but they file an aggregated report. But on a well-by-well basis, you'd never see it unless you were a reserves auditor, and then you're sworn to confidentiality, et cetera. But so what Shell did is they adopted a different strategy, and they only use short-term extrapolation, and that was actually a really good idea, frankly speaking. As we're in academia, we're trying to teach best practice. I know the second you hear the word best practice, that means it's not a best practice, but we're trying to teach you how to do things right. And probably the best thing to do is to incorporate a reservoir model. Did you do this kind of work when you were in Thailand? No, you know. Oh, you were facility, sorry. But you can imagine that in a one-slide discussion, this incorporates the entire course of 403, because what you're going to do, and I won't use I use the arrow, but what you're going to do is you're going to fit a curve, and through that curve, you're going to establish some economic parameters based on that curve. This essentially translates to dollars. So, you'll have some sort of a price scheme, some sort of a cost scheme, and you'll put that in. There's another issue that I need to get out of this mode. How did I do that? Okay. There's also an economic limit. Abdallah, do you remember that from 4.3? So let's say we said 500 barrels per day is your economic limit, although, well, I guess per year, sorry. Whatever the number is, that would be your economic limit. I didn't draw it very well. There are people who go out and they buy properties and then they reduce the economic limit. How do you do that? See, the problem with oil and gas is that it's an accounting system unto itself. It's its own. It uses certain rules from standardized accounting, but it also uses its own rules. Yeah.
Okay. All the completions and equipment downhole, they can't take that away.
No, but they could claim that they could operate more efficiently, because the economic limit is the value. That 500 barrels per year is the minimum they can produce economically. After that, they're losing money. So, Jeffrey, you come along and you say, I can drop it to 200 or whatever the case might be, and then what do you achieve by doing that? Sorry, I'm not a very good artist today. You achieve the additional area under the curve, and that can be substantial in certain cases. So again, we'll talk about this a lot more when we talk about production data analysis, but I just want you to get a feel for where this is. Now, where's the reservoir engineering behind it? There is none. But at this point, we're just talking about data and flex curves and sort of conservative curves and not conservative curves. This is 1919, so that's how they're going to approach it. Now, having said that, we come back over here, and probably the one you're interested in is this 1928 paper. I believe it's by Johnson and Baldwin, where they talk about equations. So they start talking about the first equations to match data. And we'll talk a lot more about this in the production data analysis part, but it's kind of like a bad country song. Some got to win, some got to lose. Some equations did not make the cut over history. How would you have fitted an equation to a data set in 1918 or 1920 or even 1928?
You plot points from the equation on a
Okay, but where do you get the estimates of the coefficients?
Do you have like transparent papers with preset graphs?
That would have been 1950s and 60s. And that's the same thing Sam 1 is saying, is that you would have already pre-plotted those and overlay them. That was the so-called slider method, not what you were doing with it, but actually the guy's name was slider. And then Pekovich, of course, came in after that. But very good answer. But that was the 50s, 60s type approach. I don't know how they did it. I think they must have been really good guessers. The way we do it now is we fall back on diagnostics, which is very close to the same thing we do with pressure transient analysis. We look at the trend of the production rate and its associated derivative functions, which can be calculated externally and independently, and those are used to calibrate the coefficient. So to say the hyperbolic equation, you want to know what the B value is. Well, you can calculate that directly from the data set. It's a little messy, but you can resolve that and make your direct diagnostic analysis. So jumping back to our lecture notes, again, the very first equation that evolved from this was the so-called deliverability equation. Now, we have not been talking about deliverability today at all. The deliverability equation relates rate and pressure. We've been talking about rate and time. So how would we marry rates and pressures and rates and time?
You gotta marry pressure and time.
Very good. You might just make control engineering. All right, so what's the right equation to marry pressure and time? Do you remember the Jeopardy music? No, you never had Jeopardy. And you have to answer as a question. Yes, Jeremy. Or Jeff, sorry.
Do we use the Blasingame
No,
clock?
no. I forgot to bring the duct tape. Did any of you guys bring? Do you have any?
What is
Neil, tell me.
if you're sure with the equation?
Well, sort of, but
Right.
you need pressure and time. What do you enjoy the most in Teddy 323?
Hear about?
Wow. Was that a lucky guess?
No.
He's right. It'd be the material balance equation. So we would marry the material balance equation and this, which was what we call a flow equation, and that's actually how a lot of these were done. And then you would have an equation for rate versus time. Now, there is a direct derivation of this from the case of what? Constant pressure, liquid, will give you what? No habla English? Does anybody remember? Sorry? Okay, so I'm going to jump out of one presentation and into another. Is there a simple way to turn off the screen? Well, people in the real world will still see it, so I'll leave it on. Jeffrey, what did you do good for the world yesterday?
I didn't blow anything up.
Somehow that really doesn't make me feel better. Can you be a little more vague?
I don't have a positive answer, so I gave a negative answer in which what I did it.
Okay, here we go. All right, so just like Sam 1 was saying, we take the oil material balance equation and we take the oil steady state flow equation. Now this one is not pressure squared, okay? This one is in terms of pressure because this is oil. Pressure squared is used for gas, so we'll talk about that later on. So actually, you can use the diffusivity equation to derive the pseudo-steady state flow equation. So that is technically where you were going was correct. But then we couple the pseudo-steady state flow equation with the oil material balance equation, and we achieve this final result, which is the exponential decline relationship. Okay? There is another derivation of this in Petty 620. We can talk about that as well. But this is sort of the direct derivation of this. Do you remember that, Dennis, how we would do that? We would solve the diffusivity equation for the constant pressure case. It's not easy. We have to do some manipulation, but it will actually give us an exponential decline for pseudo-steady state. Okay? So the process, we'll talk about this next week, but the process is that you would couple the oil material balance equation with the oil pseudo-steady state flow equation. Now, Jeffrey keeps wanting to talk about the so-called Blasingame plot. I apologize. I always say so-called because there were a lot of contributors. Might have been my idea, but students deserve credit. And what I did was I took the oil material balance equation and the oil pseudo-steady state flow equation. I set them equal to each other, and that generated that. Now that's on the following pages. But here, what we're trying to do is we're trying to generate an equation in rate, which means that we have to do what? Then we have to eliminate pressure. And by eliminating pressure, how do we eliminate pressure? We assume it's constant. Okay, but in the process of doing that, we have to differentiate both sides of this, set that equal to each other, solve the simultaneous equation, assume the bottom hole pressure is constant, and that gives the exponential decline. Now, having said all that, and calling back on what we were looking at before with the equations on a piece of paper, equations on a page, the exponential decline is what? It's a straight line on a semi-log paper, that is the rate being the logarithm and time being Cartesian. That's the definition of an exponential decline. It is the most conservative equation we have. It is the most conservative equation we have. So Dennis, are you going to push the exponential decline, or are you going to push something more aggressive than the exponential decline?
It depends on what I'm trying to.
Wrong answer. I don't mean wrong like bad dog, I mean wrong like things. The early time data does not follow this, does it?
No.
Okay? Because this is a late time equation.
Yeah.
So what if we marry the two? We have an early time equation and a late time equation. And we don't vary from that. We always say we're going to have something at the early time, which is perhaps more aggressive, and something at the late time, which is more conservative. And this is the so-called modified hyperbolic, or you could call it a hyperbolic exponential. So our data is a hyperbolic, so it's fairly aggressive. Then when its decline reaches a certain point, it switches to an exponential. That is the currency in the petroleum industry right now. That is almost universal. Yes.
The real production should be higher than the predicted analytical result for two reasons. First, you mentioned that was a rule of thumb in a previous lecture. Second, well, this is tangential, but I noticed that that high permeability usually controls the system even when it's low. So I use that as an analogy for the production case. I don't know if that's valid, but the higher production that you're getting should more or less control the system, in an overall sense.
Okay, so are you suggesting that the higher performance does not decay? Or are you suggesting that there's going to be a dependence on permeability as to relation of how much volume is being sampled? I'm not sure that I follow. I don't have any problem with a conceptual debate, but what I will tell you is that in the application of this, and as you'll see, the hyperbolic equation is an extremely flexible curve, and it's actually a series of exponentials would be an approximation for that. And if, for example, like we talked about, that a finite or a single exponential represents the boundary-dominated flow part, then a series of exponentials could be assumed to represent the transient part. So marrying the hyperbolic with the exponential is not a bad idea. I'm not going into the excruciating depth that I might, and maybe I will next week, but the hyperbolic cannot be directly derived exactly. Ragamon and Camacho did a phenomenal job of deriving the hyperbolic for the solution gas drive liquid case. And you can hold your hand over here and you can say, if this condition is met, then this occurs. But this condition is really pretty spongy. It is not clear to me that you ever would or should see an exact hyperbolic decline based on the assumption of a solution gas drive behavior. That's just a comment. Now, all of this has nothing to do with the flow geometry in the system. We're talking about pseudo-steady state behavior, okay? And we'll have to talk now about flow geometry, because the hyperbolic equation, as we'll talk about next week, has a very unique signature. It's essentially a power law equation at a certain point. Is there a power law behavior for production? Yes. Fractured wells have what in them? They have a flow regime which is dominated by flux into the fracture. Therefore, its general shape is linear. Linear flow is proportional to the square root of time. Square root of time would imply a hyperbolic coefficient of 2. If it's bilinear, if it's both permeability or pressure drop in the fracture and in the formation, then it would imply that there is a quarter slope behavior, which the reciprocal of that would be your approximate B value. Therefore, you'd have a B of 4, which would be much too high, but basically it's just telling you that the production is low and it's declining slowly because of bilinear flow. So we're not going to mix those two this week. We'll mix those two next week. We'll talk about that. But this week is only about pseudo-steady state. It would only be about normal, conventional reservoirs. And Jeffrey, your point about analogs is right. I would say that the issue here is a standard. The standard is fit the early part with a hyperbolic and the late part with an exponential. I was never comfortable with this. I still get the heebie-jeebies at night when I'm quiet and alone thinking this is really not a good idea, but it's an accepted practice. And I think the more cases you look at, the more you'll agree that it is a reasonable solution. And you're going, why would you compromise on this? Okay? I want to ask a very straightforward question. Would you rather have a very sophisticated answer that can easily be, to use your word, tangential, can give results which are not relevant, or would you rather have a very simple approach which may not be exact, but is very predictable in its outcome? The obvious answer is the latter. And you start thinking about the quality of data we're looking at, and it'll really be, it'll come to you like a sledgehammer. Once you start looking at actual field production, you'll appreciate that you need, something that's a functional tool for that kind of analysis. Now, when next week we talk about the so-called, I call it modern production data analysis methods, which is the so-called Blasingame method, That's where we incorporate pressure, that's where we incorporate a reservoir model. You throw all this stuff out the window, and we do it with an analytic basis. This is your so-called RTA analysis, your so-called topaz analysis. This stuff identifies itself rigorously to the reservoir model, to a simulator if you wish, and it ties the production performance directly to that. Why doesn't everybody do that? Because that is a very sophisticated approach. It requires a ton of data. I've already said that you're basically running a simulator. Those of you who had simulation courses realize how much information you have to have. It's not a simple unidimensional or single variable function like rate versus time. It's going to be pressure, time, rate, time, porosity, permeability, fluid properties, fracture properties, etc. All that stuff's going to have to be incorporated into it. Okay. Slow down, Tom. I went on a non-trip there. My apologies. Okay. So let's go back and just quickly skip back to here. And the only difference between the equations that you were seeing on that other page and the equations that you're seeing here is that this is pressure squared, and on the other page, n would be equal to 1, and so n would have to be equal to 1 here. Why do we use pressure squared for gas? Dennis, you apparently succeeded in Petty 620. Do you recall that discussion?
Somewhat.
Okay. So what happens on the next page is we will derive the pressure squared equation for steady state flow. And the way we do that is we start with Darcy's law. When we separate to integrate Darcy's law, what happens? We have something that's a function of radius, actually the cylindrical shell that propagates out from the wellbore, that's on the radius side. What happens with the pressure terms? Well, we would ordinarily assume that everything is independent of pressure, but here viscosity and formation volume factor are not independent of pressure, and so we have to incorporate that into the integral. If we integrate that, it's called pseudo pressure, right? But we can also cheat, and we can skip a step, and in this case what we're going to do is we're going to substitute the definition of the formation volume factor, and we're going to substitute that into the integral, and so we're left with an integral of 1 over mu z. And where I'm jumping to, sorry, I'm not referring to this. Okay, so Darcy's law is here, that's a standard definition. Again, the cylindrical shell that we would be looking at that would be propagating out from the wellbore would be here. So that's actually a flux area that propagates out from the wellbore that comes here. So we set that up, we solve it for rate. Now we have to integrate it, and once we integrate it, we have a radial term, which is the distance term of that cylindrical shell. And then we have a pressure term, which includes the fluid properties. That's that term. So once we substitute this into here, that becomes an integral of 1 over viscosity times the compressibility factor is the Z factor. And if we assume that that's constant, what happens then? We're left only with an integral in terms of pressure. What's the integral of x dx? X squared over 2. Okay, and so the same thing happens here, so that integral is there, and therefore the rate is proportional to pressure change squared. Why is assuming mu z equals constant allowed? Tell us from the graph. Here's mu z, here's pressure, here's these trends. If it's flat, that means mu gz is not a function of pressure, right?
Correct.
So what does that mean? It means we take it out of the integral, just like we did there, and we complete the integration. Now it is a function of pressure over here, so we have to ignore anything greater than roughly 2,000. That's the so-called Wattenbarger rule. So anything greater than 2,000 psia we ignore. So, is this a practical equation? 3 options. Yes, no, or maybe. Okay, explain your answers. Sam, where'd you work?
CCAP, our gas for.
Not where,
Where?
like physically, were you offshore?
No.
What were the pressures, do you remember?
Way above 1,000 psi.
Okay, so this equation cannot be used. Okay. Egypt, do we have high pressure gas, low pressure gas?
Low pressure.
Okay, how low? I'm
Not-
pretty sure it's higher than this.
Yeah.
Okay. Anybody else want to venture a comment or two? What's the largest gas reservoir in North America? In the Americas?
Venezuela.
Hmm?
Venezuela.
Venezuela does not have much gas. That's an interesting little conundrum. Ironically, Trinidad got a ton of gas, but Venezuela didn't. Next.
Yeah.
About 100 TCF. Okay, I need to qualify it. This is a conventional gas reservoir. It's not the Marcellus Shale, it's not the Haynesville, it's not the Eagle Ford, it's not the this or the that. It's a normal formation. It's the Hugoton. It's the Dolomite. It's in Kansas, Texas, and Oklahoma. It's 100 TCF, 85 to 100 TCF. It's been on production since the 1920s. It's 2,000 feet deep. What did your drilling and production class tell you the pressure should be at 2,000 feet deep? 0.465 psi per foot, should be about 900 to 1,000 psi, right?
Yeah, it's actually about 400.
It's 425, that's right. Very good. How'd you know that?
I did the geology project on.
Okay. So if it's 425 psi, will this equation work?
Yes.
Every day. So the Hugoton, when it was developed, people were actually using deliverability analysis evolved from that. Can you name companies that were formed by the Hugoton? Phillips Petroleum, Anadarko, I don't think Chesapeake did. Mobil and Exxon, or then Exxon. Well, I guess Mobil had a big play in it. There are a lot of players in the Hugoton, but this is where that came from. Or at least, the book I showed you by Rollins and Shellhart, how deep could you drill in 1935? What was the deepest well? Probably on the order of 8 to 10,000 feet. Okay. So the pressure should be around 3,500 to 4,000. But you come across something like this, it's 2,000 feet deep and it's sub-pressure. You can run all your reservoir engineering with this. Now, this is anybody want to speculate where you're going to find low pressure gas now?
Russia or Iran?
Why would there be low pressure gas in either one of those?
Well, they have a lot of gas.
Yes, that's what happens when you make an assumption without thinking, Jeff. Okay. Iranian reservoirs are what?
Carbonate.
You want to know the geology of Iran? They are carbonate. Are there seals formed by the mountain building that occurred in Iran? Does Iran have a lot of earthquakes? I'm trying to help you here, okay? So there's a lot of mountain building that went on historically, and some of these reservoirs have extremely high pressure because of their geologic traps. There's also probably some other reasons why some of them have extremely high pressure. The Hoof Reservoir in Qatar, which is the world's largest single accumulation of gas at about 1,000 TCF, is slightly overpressured, but the Hoof in Iran is overpressured. They just started developing the Hoof in Saudi Arabia. These would be high pressure gas. Russia is going to be high pressure as well. It's not quite Gulf Coast equivalent, but it would be similar to Gulf Coast type geology. The Olive Gulf region up in the very north near the Arctic Circle is where most of their gas fields were. At least their historical gas fields. I'm sure things are moving out into Siberia as well. What about, anybody ever heard of Turkmenistan?
Yeah.
Turkmenistan is sitting on an ocean of low-pressure gas. An ocean of low-pressure gas. Who do they sell it to?
Russia.
Wrong.
Well, China, but Russia. Sorry.
You know, so I was trying to teach my daughter algebra, and did I tell you guys this? She broke her pencil, threw her book at me, and ran off screaming, right? And so we got a tutor, and she's a lot happier. I'm a lot happier. Her grades have gone up. And my son remarked that he heard me say to her 1,000 times, think, stop guessing. Okay, so Jeffrey, I'm going to treat you like my daughter. Think, stop guessing. Okay? Why would they sell gas to Russia when Russia is one of the world's largest gas marketing countries?
The thing is, they were part of the Soviet Union, so all the infrastructure had to be geared towards the
If you
main
look at a map lately, where's Turkmenistan?
It's China.
Stop guessing. What are the borders of Turkmenistan? The Caspian Sea, Iran, and Kazakhstan. It's nowhere near Russia. Sorry. I'm you. Do you know who my role model is now? It's Yosemite Sam. Do you remember Yosemite Sam? When he'd go crazy? You okay, Sam?
No.
You don't like Yosemite Sam? You don't remember Yosemite Sam?
Looney Tunes.
Yeah, thank you. I'm asking Jeffrey. You don't remember Yosemite Sam?
I think I might have seen it.
Let's do a quick map search. Does that help? Where's China?
A few countries east, southeast.
All I gotta do is build a pipeline and somehow it gets to there.
That project has been around for a while.
Are you from Pakistan? No?
Yes.
Okay. Have you ever heard of this road here? It's KKH Road.
Mm-hmm.
It's amazing. It's the world's highest road. Yeah. At any rate. Yep. Okay. So, all the Russian gas fields of any consequence are up here. And over here. I think I got that right. Is this the OPCO? Give me something. How do you make it label it? I guess there's nobody there, huh?
You might want to try Continental Europe to see if you get any kind of label at all.
What did I just say? OPCO. It's not the OPCO. It's over here. I got a better idea. Gas field in
That's funny.
This is where I was thinking. Over here. Did I just do that? I really did, didn't I? So, is this Russia? Looks like Russia. Yeah, they're up here. Thank you, Jeffrey. As usual, my blood pressure is now back up to where, you know, basically I could die at any moment. So now we talked a little bit about deliverability testing, and every discussion of pressure transient analysis usually has some discussion of deliverability testing. Why? What do you think when you hear the word deliverability?
Money.
Okay, explain.
Well, deliverability implies, hydrocarbons produced or to be produced, and that equals money.
Okay. Next guess? Yes.
I'm guessing because deliverability has to do with flow rate, and flow rate has obviously to do with permeability, and permeability has to do with such things.
Okay, so let's pretend that we are 100 years ago, and that we are beginning the oil industry, and we need to have standards. The word deliverability means how much can be delivered. Okay, that's easy enough. We could say production capacity or something like that. Now, how would we compare individual wells? What would be a good way of comparing individual wells? Yes.
How much productive capability they've had, and how much you think they will have.
Okay, good. Now let somebody else talk. Anybody? Go ahead.
Measure how much that unit or well produces and amount and volume of specific conditions or mass.
Okay, keep going.
I know this from hindsight, but they measure it using energy, how much energy it could produce.
No, I mean, but I'm thinking in very simple terms.
Productivity.
What would, sorry?
Productivity.
Productivity index isn't going to help us, it's going to help us compare well to well, but it's not going to help us define the maximum capacity. Okay, I just gave you the words that I want you to tell me back, okay? So what I want to know is what's the maximum capacity of this well. I achieved that by using what's called the deliverability test. And I achieved that, or I utilized data from that. For example, let's say I control the rate. So we'll pretend that this is Jeffrey. He's got his hand on the valve, standing here, and he's opening up the pipe, and out comes some gas. Here, why don't you smoke a little bit, Jeffrey? Okay, so there, and so he's producing gas, and the first rate is here, and then he opens the choke a little more, and the second rate is here, opens a little more, third rate is here, opens a little more, fourth rate is there. Everybody got that? Why are the steps equal?
Because he controls the rate.
Well, they don't have to be, but again, we're trying to come up with a standard. So if you're going to change the rate willy-nilly, it's going to make things a little difficult to interpret. So let's do things consistently. Why are the steps the same? Neil? The rate's constant, so it doesn't matter. The pressure needs to do what, class? It starts, and it needs to stabilize to that point. And then it needs to stabilize to that point. It needs to stabilize to that point. It needs to stabilize to that point. So you've got 4 rates and 4 corresponding pressures. What kind of pressures, Dennis? Stabilized pressures. Okay? What does that mean?
It means they're not changing.
Okay, and at what condition do the rates and pressures relate to each other where they don't change? Am I going to play? Okay. That's where we would have a constant productivity index. That's where I was going. Okay? So you could use the concept, the productivity index is the rate divided by the pressure drop. So when the rate, and this, I'll show it. So if I take this distance, this is delta P. So if I take Q1 over delta P1, Q2 over delta P2, etc. And what I'm trying to do is get a constant for each one. And that's why we would let it run until it becomes constant. Now, I'm not going to worry about the productivity index, but I am going to worry about the pressure drop squared. So that's this number, PR squared, minus this number, which is PWF squared. So each one of these, that's going to be that, and of course these are your rates. Okay. And so here's a point, here's a point, here's a point, here's a point. I know it doesn't look like that, but I'm the one with the pen, so I get to do what I want. Okay? Now, that gives us a relationship on a log-log plot that just keeps going on forever, right?
Does it?
Well, the line does. It's an extrapolation. Okay? Now, what I need to know is what is the maximum production potential from this well. So what is that going to look like? Well, we then substitute a zero sand phase pressure into here. So this is PWF equals 0. And we read along this line, and we drop down to this axis, and that gives us the so-called absolute open flow. Okay. Why is that important?
That's what you ask for, the maximum potential for a well.
That should be unique to a given well. I'm not saying it is, I'm saying, like our logic, is that would be a fingerprint. Because for that well, for those pressures, for those fluids, for that geology, for that completion, that's that.
How did you define?
But this is a little dangerous because you start playing with this and you start to believe it. I've got a friend of mine who everything is CAOF, computed AOF. Everything is, that's not where I want to be. Because what's wrong with the computed AOF? It assumes you know the correct reservoir pressure. That's actually the only variable that's really standing out here. But if you don't have a good estimate of reservoir pressure, and if you don't have good estimates of bottomhole pressures for this, if you're using surface surrogates to do this, it may not be particularly good.
How did you define the zero sand phase pressure?
You just pull 0 out of your ears. You're saying that the maximum flow rate would occur if you could put a vacuum on the formation. Okay. It's a fictitious number. Okay. Yes.
How come this flow test you're making it dependent on making the denominator dependent on delta P when for this one I think for figure C we're using a gas system, so the Q equal the relationship is P squared.
All of it is P squared, yeah, for sure.
But if the test that we're doing is in increments in which the variable we're comparing is Q over delta P, then
No, I didn't do that. That's why I erased it. It would be Q over delta P squared. Really. Is that where your correction was? Sorry, that's fine. So everybody's happy with this? We each have a well in this room. Our location in the field is as we sit right now. Okay? I'm the government. I come along and I say, what is your AOF? You must calculate your AOF once a year. You have to go out and you have to do this test. Okay? Why? Because all of you are given an allocation factor. You cannot produce more than that. Why? This is pseudo-steady state. What happens if you produce more than your neighbor? You're stealing his fluids. The drainage area realigns to whatever the production rate is in a perfect sort of system way. The government invented this simply as a legal way of assuring that nobody cheated. They had no idea what pseudo-steady state was. They had none of this had even been invented. None of the concepts. Nobody was using the diffusibility equation. Blah, 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 blah. But the idea of testing a well, getting a maximum theoretical flow rate, you turned it into me, and I look, and yours is higher than his, but his is higher than his. So what do? I've got to cut you both back. Otherwise you're going to steal from him. Then there's no well in the middle. What about the property owner in the middle? See, that's the problem here, is that people own the property in this country. They own the assets. They own the resources. So let's say it's yours. How do you feel about that? You want some sort of a guideline where he's not taking your food. And again, nobody thought about this. What's the legal distance that you must be from your neighbor in Texas without a waiver? 330 feet. Now you can get a waiver. You can agree on it. You can fight over it. You can sue each other. But somehow, because the government wants it, the state wants the revenue, they're going to come up with a formula that says you can be 127 feet from the property line, but now I'm going to limit you to 2 million cubic feet a day. And somebody will arbitrate that agreement. There's not a lot of proration left in the United States. But this was really big in the 20s and 30s. Do you remember all the pictures of how people drilled wells? They were all right on top of each other. That's what this is all about. Okay? And from that came the first well testing approach. Everything we've talked about so far has only to do with production rate. Then what do we do, Dennis? What's our favorite rate? 0. What happens when we shut in the well? The pressure goes up. Sorry. Neil? What is this pressure rise a function of? TWF is equal to a function of what? You're a chemical engineer, right? Okay, so I'm going to have a little seat so my back can say, stop screaming at me. Sorry? It's not equal to not equal to a function of flow. It is in a way that's the nonlinearity in gas and spongy liquids, but for the sake of argument, for liquid system, it's not equal to a function of rate. But it is equal to a function of what? You want to throw a lifeline at Dennis? Sure. Dennis? What's the biggie?
Permeability.
Correcto. What next?
I know it's
All the other little things. Porosity, viscosity, compressibility. What else? Thickness. What else? Formation blotting factor. What else? Did we get them all? And then there's something. You remember the something we talked about? The leftover term? what did we call the leftover term? And we called it the trash can. Not in this course, but in 620. What's the name of the trash can? Abdallah? The skin factor. The skin factor. The skin factor is a leftover pressure drop. So we don't know what it is. We think we know what it is, and there's a whole bunch of people that tell us they know what it is, but we don't really know. We can calculate it, but we can't really figure out what it is. Okay, so this pressure buildup test, will it go all the way back to original pressure? Yes, no, or maybe?
Forever, if you do it forever.
Is that right? If you took mass out of the system, would it go back up to original energy?
Well,
The answer is no, Jeffrey. The answer is no, Jeffrey. The answer is no. There are a few absolutes, and there are a few times when I won't let you debate, but the answer is no. If it is a finite volume of mass, and you take some out, it cannot go back.
Even if there's a drive from outer source, like
no. We're not.
I'm gonna start calling you Jeffrey Jr. now.
We're not assuming.
Okay, so there's a drive mechanism from outside. Give me an example. Okay, can you prove it?
Without scrolling? Well, actually,
I have no objection to that. Will it look unique? Are you sure? I really love my job. I really do. All right. So for the sake of argument, everybody understands deliverability testing is only about estimating a relative number so that we can compare it to each other. Now, this is 2013, and this was done back in the 30s and 40s. Can we analyze these data as a pressure transient test? Can we analyze these data in detail? Can we do more than a deliverability plan?
Theoretically.
Theoretically, we definitely can, but in reality, why?
Because their measurements are very exact.
Okay, which measurement?
And the frequency.
Which measurement?
Well.
Which measurement?
Flow rate of it.
Wrong. Flow rate we can measure.
How we said the pressure is constant.
Okay. But can we keep the flow rate constant?
I thought we did for that part of it.
Sorry?
I thought we have some data when Q is equal to 0 and we have pressures.
Yeah, but that's out here. I'm talking about within the green cloud.
Oh, no.
Okay? Only within the green cloud. You're going to have a problem keeping Q constant at each step. That's really tough. Okay? And also, as we mentioned, measurement of these pressures, drawdown pressures are difficult. Not impossible, but difficult. But if you had accurate rates here, 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 and here, I'm not saying the 7 decimal places, but let's just say very accurate, and then you had accurate pressures here, is there any theoretical difference to the reservoir for that or the rate equals 0 time? No. The problem is the measurement. Okay. So here, measuring Q equals 0 is pretty easy. You shut in the valve, or shut off the valve. Okay. And then you follow the pressure. Okay. So the rest of this discussion on pressure transient testing today is going to be about what, Dennis? Estimating this and that. Generally, in conventional reservoirs, our objective is permeability and skin factor. All right, so very quickly on this. God, I gotta remember to check this. It's like I got 10 versions of this, and it's all always goofed up in Fonseca, but that's all right. So I wrote that the focus is on the reservoir, and the reservoir is down here, but we also have to consider the completion. So what happens if you have a leak in the tubulars and gas goes? Do we have leaks?
Yeah, we do.
All the time. Okay. What else can happen? What if we have oil and gas being produced together? So there's an oil column in here, and there's a gas bubble that's pushing it down. What happened? I want you to think about this for a second. This is a very unusual effect. So you have an oil column, let's say, that goes to the top, that's shut in. You've got an oil and gas column that goes all the way to the top, a little bit of gas, a lot of oil, like that. What happens when you shut in? The oil falls down, right? Or if there's no movement, it'll have to be displaced. And so actually what happens is the gas segregates and goes up. You can see there's a packer here, so it'll fill up behind here. And it goes up, and it rises up as a bubble. What happens to okay, when a bubble goes up, when you watch it get from getting small to getting larger, what's happening?
Pressure drop. Pressure.
More specifically, the bubble expands because of the pressure being lower, right? The higher you get, let's think about, the ocean perhaps. At the bottom, you release gas, and the bubble's small. When it gets to the top, it's huge. Why? Because it was allowed to expand. Okay? It's in pressure equilibrium with its surroundings. What happens if you take that bubble from the bottom of the ocean and you don't allow it to expand? Then you get full pressure at the top of the system. And I understand that's not going to happen in the ocean because the ocean's unconfined. But what happens here is you end up with a bubble of gas at the top that has not expanded. And what's its pressure? Same as the bottom, or close enough to the bottom pressure. How can it expand? Well, what happens is it pushes the oil back out into the reservoir. That's some sort of a backflow mechanism. That's the only way it can relieve itself, other than to blow the wellhead off. You do a quick calculation on this, these pressures can be tremendous, these bubble pressures. Generally they're not, because it's not just one gigantic bubble, but it can be huge. And it actually creates a hump in the pressure signature. The pressure signature goes up and rolls over. It's a huge hump, and it's that bubble effect. Okay. When you have a bubble effect like that, how do you interpret the reservoir signal? Because all this action is happening in the wellbore. Anything that happens in the wellbore is connected to the reservoir. So probably it affects what's happening in the reservoir. So what do we have to do? We have to wait until this effect goes away. I've seen people analyze pressure transient tests, analyze this effect rather than the reservoir. When you analyze the pressure transient data set, your expectation is that you're analyzing the performance of the reservoir. But in actuality, in this case, you'd be analyzing the performance of the wellbore. The same thing happens when you have a leak. What's an easy way to tell whether something's happening in the reservoir or the formation? If there's any kind of a spike, it's definitely the wellbore. Okay? I've seen packers, like right here, slip during a pressure buildup test because the pressure is building up and the pipe slips within there and fluid is allowed to go in the back. And at first it looks like a leak, but it spikes up. Now, I know you're saying, well, that's pretty cool. No, it's not. Because it just ruins your test, but that's all right. And then the fluids themselves. So is everybody okay with this? You can have all these different effects in the wellbore. And what does it mean? It means you're not analyzing the reservoir. You're analyzing the wellbore if you try to interpret that data. Just something to be aware of. Yes?
So if slippage like that happen or anything, will it appear on your well test in the early time so you can distinguish?
Yeah, it just looks like a spike. It's like a 5-minute surge. And I mean, it could be something else, but that's the only thing I could think of that the packer probably slipped.
So does it ruin the rest of your well test?
No, in both these cases where it's just a temporary few-minute spike or something like that, it'll definitely make your hair stand up because you don't know what it is. But the bubble system will ruin your well test. I looked at a case recently where even after a month, the bubble is still not settled down. And I mean, that's obviously a very low permeability system, but it basically renders the test useless. So, you know, you have to realize, though, that you can try to go back and use theory to resolve this, but when you don't know what's on the other end of the problem, you're wasting your time. Unless you can tell me how much fluid is being produced or injected into the formation during this bubble rise, which you can, unless you have a gauge at the bottom, there's no way. You can't resolve this. I mean, if you look at the difference in surface gauge data and downhole gauge data for things like shale or even you know, these liquid rich systems, they don't look anything alike. Why? Because what's going on at the bottom of the well is completely different than what's going on at the top. Just, you're asking too much to try to compute through it. I mean, you know there's all these algorithms in Prosper, in, I forgot the name of the Schlumberger product, but you've also got Olga now, and, you know, there's all these algorithms to calculate this stuff. But you're calculating things where you don't know what's happening on the other end. By the way, these are analogous to pipeline type calculations where you turn it and go vertical. But if you don't know what the conditions are at the other end, it's practically impossible. Next slide. Everybody okay with that? Okay, so what do we need? And I'll just sort of point out that in pressure transient analysis, we have these data processing for permanent gauges. I wrote this about 10 years ago, but still figuring out how to incorporate permanent gauge gauge data has really become an issue. There's a few people working on this, but mostly what have the vendors done? Okay, let me give you an example. You're taking data every second, 86,400 points a day, 365 days a year. How much data is that? Let's just make it easy. 100,000 points a day times 400 days. What's that?
40 million.
Okay. 440 million points. What are you going to do with 440 million points? Is that going to fit on a flash drive? Maybe. Depends on which one it is. Okay. So what do the vendors do? They load the data set in pieces. They tell you, I'm going to load day by day, and I'm going to let you inspect, and I'm going to let you reduce the data set down. There's just no way you can handle that much data. That's an exaggeration. Most gauges are probably going to be taking data every 5 to 15 seconds. So you went from 400 million to 100 million, or maybe 30 million.
For one well.
Yes. for 1 year. And does all that data have information in it? I'm not sure. Some of it could be corrupted. There's error in everything. Okay, now numerical modeling, and again, these are a little bit old, but I was advising caution because the couple between numerical modeling and pressure transient analysis has always been kind of dubious. You have to have a very high resolution numerical model to do pressure transient analysis. A lot of your colleagues who were in graduate school 35 or 40 years ago wrote simulators to generate pressure transient tests. Why? Because that was a way of calibrating the code. If it could reproduce a pressure transient test, it's probably okay. Variable rate analysis is deconvolution. I know you guys hear that word and get all excited and you think the deconvolution is going to save you. It's not. Deconvolution, as it's being applied right now, captures the buildup. Deconvolution, as it's applied right now, captures the buildup. And this one more time. Deconvolution, as it's applied right now, captures the buildup, not the individual drawdown machine. Why? Why is capturing, or why is focusing, or why is solving on the buildup better than solving on the drawdown?
You know the rate.
You don't have rate errors. Rate errors in deconvolution will spin it off into oblivion. Okay. Better data analysis functions. This was, again, written a few years ago. We introduced some new functions about the time I was writing this, some derivative functions and some ratio functions where you try to use it as diagnostics so the data basically analyzes itself. Production data analysis, we haven't talked this much about that yet, but we'd like to have better consistency between rate and pressure measurement. We've talked about that before, that the frequency of the two aren't the same. We'd like to have better conversions of surface to bottom hole pressures, but realistically, the vendors will provide that. I'd like to see further implementation of semi-analytical solutions. There was a paper written in the mid-2000s or early 2000s by an individual who said, we don't need these complicated functions anymore. We're just going to numerically model everything. Okay? Is that a good idea or a bad idea? It just is what it is. Now the vendor that implemented this, you have a tab, you push one, it's analytical, you push the other, it's numerical. That's easy enough. But there is there's man-centuries or man-millennia of programming that went into making sure that the computations and the numerical part are as accurate as the computation in the analytical part. We knock some things off doing the analytical solution, right? We make assumptions about things, and then you don't want to honor those assumptions, so you want to do it numerically. But you still have to be able to produce a solution that has the near accuracy of an analytical solution. That's what we're talking about here. Diagnostic methods, again, this is sort of how do you compare data and how do you identify the model. Okay, so there's 10 of us in here. How many reservoir models are there for pressure transient analysis? Start counting on your fingers. Ready? Baracho, give me a model. Do the radial flow. Okay?
Linear flow.
Okay, so you're thinking about a block linear system or a fractured linear system?
Fractures, that's what I
Yeah. Okay, but we'll give you two because there's a block linear system as well, right? Can you think of anything?
Bilinear flow.
Bilinear flow would be along the same line as Tim. In this case, your fracture is going to have permeability. In this case, your fracture, if it were infinite conductivity, is infinite permeability. So there's three models.
boundary flow.
Okay, so now you're going to put boundaries around it. None of you mentioned boundaries, but I can put boundaries around anything. So now we have boundaries. Next.
Spherical.
Okay, you could have spherical flow. There are not a lot of spherical wellbores. I'll repeat that for effect. There are not a lot of spherical wellbores. One more time. There are not a lot of spherical wellbores, but do we use spherical flow?
Yeah.
If yes, why?
Perforation?
Very good. Can you explain?
No, because King just said perforation, and I just said that.
So Professor King just said perforation and no more. Okay. Are there other instances of where you would see spherical flow? Spherical flow means that you put a point in the reservoir and you cause fluid to be produced into that point. Can you think of something that would have that? Could there be a special elevator that you go into it and magically get transported somewhere else? No. It would have to be some sort of a conduit, like Jeffrey's suggesting, with a perforation, or what? Does anybody here work for Schlumberger? How much money do they spend on research a year? Their number's always $500 million to $1 billion. Okay. That's with a B. They developed a tool that would drill a hole into the formation and allow you to put a probe in. That's your spherical flow. So if you can drill a hole into the formation and produce fluid out of that probe, that would be a spherical flow type reading. So continuous measurement equals continuous assessment. Continuous measurement equals productivity optimization. It seems like a play on words. Why do most people monitor production data daily? How many points does Exxon collect around the world? Rough guess would probably be 10 billion. I'm guessing, but that would be my estimate. Why are they doing that? When you pass an oil well out here in Texas, there's always a solar panel and some sort of a cellular phone type transmitter. Why is that?
Transmitting data?
Okay, well, why is it taking data?
They needed to manage.
Who's they?
The operator needed to manage.
The operator of the field or the operating company?
The company, they need to manage.
Okay, but now you've gone into the gray area. I wanted you to say the individual. Who's looking at that? Is it someone in Houston or in Bangkok, or is it somebody in the field?
Field manager.
Okay, so it's the field. So why would you be monitoring for the field? Neil? Chemical engineer? Very linear?
I don't know.
Okay. Maybe you do, you just haven't thought about it. What's the first thing you hear when you get up in the morning?
Alarm clock?
Okay. So most monitoring or measurements are about alarms. Something went wrong, something that changed, something that should have not happened that did. So the genesis of all this production monitoring was really about alerts. Okay. But now what I'm telling you is you can actually use it to optimize your production. Now there's a lot of sayings in the oil field. One of them is you can't make a bad well good, but you can definitely make a good well bad. So interpreting that is that something bad happened and it could never recover. There were examples of people wanting to get in the newspaper with their deliverability testing and turning the rate way up, and what happened? They did damage to the formation and the rate could never be recovered after that. They got a 10-minute flow rate of 10 million cubic feet a day, and when they put it back down to the proper choke setting, it was 1/10 of that, and it never got any better, as an example. Yes?
In this slide you said deconvolution captures buildup. And I don't know what deconvolution is, but from what you said, I understood that is a problem. You said that's a problem because we can't measure rates accurately.
Okay, so deconvolution is pressure drop in the well is equal to an integral from 0 to T of the rate function, actually it's the rate derivative of tau, which is a dummy variable of integration, and then delta p, which is constant rate, the actual model, t minus tau, d tau. Now you're looking at that going, I have no idea what you're talking about, Tom, right? Okay, so this is the input signal, this is the rate profile, this is the reservoir model, right here, okay? And this is the output. So, input, output, constant rate. And then this is the model. Okay, no problem with that. Very high level in theory. You don't like this. Have I made you uncomfortable?
No.
Okay. So this is too abstract? All right. Never finding what you're looking for when you're looking for it. Where are you? I can smell it. I'm getting close. All right, how about this? Does this make better sense? So, this is our calculated pressure. These are dimensionless, but they're rates. This is dimensionless, this is our model. Okay, so this is the model, this is the stimulus or the rate. Okay, it's just something we input. Okay? And so what happens is, in deconvolution, you measure the thing on the left. That's the output. So you're actually measuring this output. And you know the stimulus. So what do you want? You want the model. You want the undistorted underlying behavior. Okay? How do you trick this and solve it for the model? If you don't like how this looks, you know, we can write it in X's and Y's and that sort of thing.
No,
Just think about it as input function, output function, generating function, model. Okay? So we know the input function, we know the output function, we want to reverse calculate
and get them off.
the model. Now you can take this equation, this one right here, and you can expand it term by term, and you can solve it by regression. Recursion, my apologies, okay? And where is that? It's not in Russia. Who's that sexy guy? Dr. Lee told me I look like a gangster. Can you believe somebody tell you that to your face? Okay, so there's this guy's PhD dissertation. And it's down here in one of these appendices. It almost looks like this guy knew what he was doing, right?
Oh, wow, what is that? Line stop? What is a line stop?
Yeah, here's the recursive form. So exactly like we were just saying. If you think I don't know what I'm talking about, I've lived it, pal. So you solve this thing backwards for the model. Ready? When you solve something forward, is it stable? Generally speaking, mathematically, yes. When you solve something backwards, what happens?
Constant, non-uniqueness, crazy stuff.
Somebody say it. It's unstable. So on the forward process, you can have error in your stimulus. It'll be multiplied by the model, and out will come on the other side, and it's very predictable. Now you have error in your output, error in your stimulus, and you want to reverse engineer the model, reverse calculate. So guess what happens? Not only do you have the problem of having the error, but any errors magnify, and they magnify in a cumulative sense. So this is a waste of time. So the reason they went to solving deconvolution only on the buildup is because there was no rate. So that eliminated that term. In layman's terms, that's why they did that. You still have this god-awful problem of instability. How do you get around instability?
Make sure your pressure gauges are good.
Wrong, wrong, wrong. You hate when I say you're wrong, right? It's not that it's wrong. But how would you get around instability? What's rule number 0, Tim? Cheat. How do you cheat? You impose some sort of constraint on the algorithm where it does not allow it to go crazy. Okay? What happens when you impose a constraint on something? You were saying it's non-unique. So you've already done that. That means depending on how hard you crank the constraint, that's going to affect your answer. Also, how do you solve these things? They usually use regression. They're not explicit. You cannot reverse solve it. Now you could the recursion approach. And the whole dissertation I just showed you was using Laplace transform. And you could use the Laplace transform. But what's the problem with Laplace transform, Dennis?
You can't go back.
Easy to get in, impossible to get out. So everything's okay. It might be erroneous in the Laplace domain, but then when you try to reverse out, what happens? It magnifies the error. So deconvolution, I realize I've spent 10 minutes being extremely negative about deconvolution. I wrote thesis and dissertation on deconvolution. I've had 2 other students write theses and dissertations on deconvolution. I'm not upset about it. I just think we need to stop and realize that deconvolution is going to have very limited applications in what we want to do. Okay. And I would rather chase the other end. I'd rather chase trying to diagnose the model, trying to interpret the data, trying to do these other things, than trying to reverse engineer this problem, which is going to give me what, Jeffrey?
Non-unique.
A non-unique body of information that I'm then going to try to fit with a model or try to interpret or that sort of thing. And I know if Dr. Gringarten were here, he'd be screaming that, shut up, you don't know what you're talking about. I know that Dr. Leviton would do the same thing. But my personal feeling is that deconvolution is in the vendor software. If you want to use it, it should be robust enough to use, but you have to follow the rules. You have to apply it where you know you have a fixed point in space, and that would be something like a build-up. And I don't want anybody on the receiving end of this and the distance learning to believe I was yelling at you saying wrong, wrong, wrong. But the problem with deconvolution is that anything that disrupts the system becomes an amplification of error. And it will take a little bit of noise and turn the whole thing into garbage like that.
How does it have just an amplifying effect? Is that something systematic to the algorithm itself?
It's not the algorithm, it's the relationship. When you're looking at, and I closed the other file, but when you're looking at the convolution, which is a mathematical, what we call it, identity, I guess, it has a very specific behavior. A convolution would be like a filter, if you want to think. I guess technically that's what it is. And convolution takes 2 signals and provides a third. Okay? but it does so in a forward fashion. If you take that filter and try to reverse it, what do you think is going to happen? It's just going to be a mess. That's where the instability comes from. And granted, I want to be very candid about this. Deconvolution has applications in other fields, but they have fixed behavior that they can latch onto. Deconvolution is used in seismic. I don't know what its context is, but it's not the same kind of a problem where both signals are distorted. It's some sort of an analytic type behavior. Analytically, if you want to do a thesis or dissertation on deconvolution, analytically, no problem. It's probably already been done before, but you can give it a good run and do a thesis or a dissertation on that. But I will guarantee, if I add 1% of random noise, your algorithm is going to buck like a Bronco. That's what the problem is. Forward, very predictable. Backwards, very unpredictable. Okay. All right, so the questions to consider: what do we want to estimate? What did we already say, Dennis? Permeability, skin factor, fracture half length, and then dual porosity reservoir properties. Now, can we have a model that has all of these in it? Can we have a radial flow model with a hydraulic fracture and dual porosity? Yes. Okay? So that's 5 parameters being matched from a system of data that has what? Pressure and time. Okay, is 5 parameters too many? Think about how you want to try to estimate one thing from another. Every time you add a parameter, you're asking more and more of that signal to give you something. If you do not have part of that signal,
Code Maroon test. This is the monthly test of the Code Maroon system. No action required at this time. This is only a test. 1:45 p.m.
well, that at least tells us what time it is. Okay? If you do not have radial flow, can you estimate variability? No. If you do not have linear flow or some sort of a fracture flow regime, can you estimate fracture half length? No. If you do not have a transfer flow regime, like you do not have some sort of a component of dual porosity behavior, what's going to happen? Those parameters are going to be meaningless. No matter how smart you are, no matter how hard you try, if you don't have a part of the signal that is represented by a parameter, it's junk. Every student walks up the software, turns on all the parameters, turns on the regression, and pats himself on the back, and they forgot that if you don't have part of the signal that represents permeability, you're done. If you don't have part of the signal that represents fracture half length, you're done. If you don't have part of the signal that represents dual porosity reservoirs, you're done. The results are garbage. Now, I never say anything about the skin factor because the skin factor is the leftover term. It's an additional pressure drop that's basically just an error. Unfortunately, we have become very comfortable with the skin factor. It is I call it the trash can, you can call it the suitcase. Is the skin factor time dependent? 3 options. Yes, no, maybe. Somebody take a position on each one.
No.
All right, explain no.
The skin factor, you can always see it, and
It's always a constant differential.
yeah.
Okay, so you're very linear. You don't believe that it could ever vary. Good. Okay. I'm torturing you a little bit. Next.
Yes. You can have damage build up, and that would change the skin factor.
Okay, can you give me anything else?
Um,
Okay, so you're saying that damage gets worse with time.
They can get
Okay, so that would be a great example. What would be a cause of that?
ion migration.
Asphaltene, gas blocking, condensate blocking, anything else you can think of?
Even well stimulation or anything like that where it gets rid of the damage.
Okay, so you could have multiple stimulations that would actually reduce the skin factor over time.
So anything.
Probably not gonna manifest itself quite as nicely as evolving damage, because it would be step changes, but theoretically, I agree with you. I had a field project one time, that they would acidize. It was a dolomite, limestone dolomite, part of it was dolomite, part of it was limestone, in, Alabama. And I know you don't think of Alabama as being a petroleum producing province, but there's some, really prolific, limestone dolomite reservoirs that are trapped. And this one, they would acidize the wells every year, and it was just like you hit it with a hammer. The production would shoot up. Well, Smith Oil Company, notice, the name, right? They bought it, and they decided they didn't want to do that anymore. And what happened? So, you do not perform field maintenance, bad things are going to happen. Their point was, when we were talking to them, that they made $1 million a year doing nothing. Except that you could make $5 million a year if you did something. And they said $1 million a year doing nothing is better than, it was just, the logic was just unbelievable. But that's their problem. Okay. What about maybe?
I like maybe.
Okay. You would. I had my brain map this week, one of these special things, find out what kind of team player I am. Turns out you don't want me on your team, no matter what. And not even people like me get along with people like me. I'm not a weeds person, I'm a subatomic particle person. And the people that convened the meeting, they were all stratosphere and outer space people. It was very interesting, okay? So, no, yes, cloud person, explain maybe.
That depends on what.
Move the time, we only have 10 minutes.
Oh, okay.
And minute for minute, you've consumed yours, so go ahead.
What was the question?
Maybe not. He said skin factor does not change. You said skin factor does change, and you said maybe.
Right. Well,
Okay,
both are
it's okay, Jeannie, stop guessing, okay? I'm good. Jeannie's my daughter, that'll be your new name. Stop guessing, okay? No, I can't do that. That's sick. Okay, so, productivity, efficiency, damage or stimulation, we just talked about that. We have a direct assessment using pressure transient analysis. And by the way, whenever I said that we should not be doing pressure transient analysis in shales, I confess I was wrong. This is 5 years ago. I said, don't waste your time, blah, blah, blah. But you can do productivity assessment. You can see whether the well's damaged or stimulated, or how it's damaged or stimulated. That's fine. You should do this. I just think you need to be realistic, going back to this, about what you're going to get. You're not going to get permeability from a well test in a shale. It's not going to happen. Reservoir pressure, initial or average. Now, unfortunately, that means you're going to have to be shut in for an eternity. How long is eternity?
A very long time.
Yeah. Do you like eternity?
No.
Then,
Shut up, Gene. Okay. So, do you believe you're going to perform a pressure shut-in long enough to see average reservoir pressure in 2013? Yes, no, or maybe?
Not in unconventional.
Give me a conventional example.
Saudi Arabia.
Okay.
Maybe Saudi
But
Arabia.
to them, a long build-up is 24 hours.
No.
Maybe. But more likely, it would be an injection fall-off type test. There's a lot of that being done, where instead of using a producing well, you use an injection well. They might take some wells offline for whatever reason, maintenance, et cetera, So we used to get a lot of really good tests on a project I had out in West Texas. And the nice thing about West Texas wells they're not shales or anything like that, they're just low perm, like 0.01, would be the minimum, maybe 0.05 or 0.1 type millidarcy permeability. But the wells did not go on vacuum. They would hold pressure, which meant you could measure the pressure at the surface, and you have a problem with water, and you can use that. That was some excellent test data. But generally speaking, in a production scenario, you're not going to shut the well in long enough to see that. What are the major complications? Planning of the pressure transient test. You always want to model this. I was in a meeting recently where, you know, good and evil. The guy who was wanting to do the test just said, I'm going to go open and close the valve, I'm going to take some pressure measurements, and I'm going to show management how smart I am. The other guy is saying, well, you know, you need to design it, you need to create an execution plan, you need to stick to the plan. And I felt like a referee at a bar fight. You know, that's the kind of behavior you're going to get. If you know, whatever the old military thing was, a failure to plan is a plan to fail. If you do not design your well test, and it is so easy now, you can do it in 5 minutes, generate 50 different scenarios, and convince yourself, okay, I'm within this window. You don't do it, you're flying blind. You have no idea what the answer's going to be.